We will go through 10 plastic parts design guidelines for successful production because nowadays we can see that most of the industry is widely using plastic components, and plastic components are manufactured by injection molding, extrusion, blow molding, or machining. Even there are different manufacturing methods being used to produce relevant plastic components. So this 10 plastic parts design guidelines are specifically for the injection molding, so we'll go through one by one. First is surface finish selection. Selecting a part surface finish is one of the important parameter because different products require a different level of surface finish. Basically, the surface finish can vary from high gloss to rough texture. A glossy finish can enhance the appearance of the part, while a textured surface may help to mask the zinc marks or parting lines or any kind of defects. Surface finish should be specified so it does not interfere with the ejection of the part from the mold. The smoother the finish, the more easily the part is ejected from the mold, and extremely rough surface it will cause difficulty to remove the part during the ejection process. We'll see some of the images. So you can see the plastic pieces, which shows exactly the different level of surface finish from glossy to texture. And next is material consideration. When you choose a material for the component for a product, you may need to evaluate multiple parameters. You should be knowing where the part is going to be used and what kind of environmental conditions it has to withstand on all these parameters. So you will be considering the temperature, the chemical resistance of the material, and the agency approval, because specific countries require different agencies approval to release the product in the particular market, and the assembly feasibility, the required finish you wanted, and also the cost and availability in that particular region. Next is uniform wall thickness. A non-uniform wall thickness causes dimensional control problems, and also it causes problems such as warpage and shrinkage and different defects associated with that. Also, the right wall thickness, the maintenance of the right wall thickness will help uniform filling of the molten plastic during the injection molding process. Also, some materials can flow through thin wall sections and give the proper strength for its application. However, some materials do not move freely through a certain thickness. So you need to consider what material you use and basically design the wall thickness according to the viscosity of the material. The thicker areas tend to cool more slowly, and there is a risk of voids or shrinking defects on thickened areas. So you have to try to avoid the thickened areas. Try to maintain a same level of thickness throughout the part region. A good rule of thumb is to design all parts across sections as thin and uniformly as possible. The use of ribs is an effective way of achieving rigidity and strength while avoiding cross-sectional thickness. Here you can see some of the examples which demonstrate the correct and incorrect way of designing the plastic component. The left hand side you can see the part is having variable thickness, and the right hand side the uniform thickness is maintained across the part. Here is another example. You can see the correct and incorrect way of designing a plastic component. Next, the radius in the corners. Radius should always be a consideration in regard to the part's thickness. The general rule of thumb is that the thickness at the corner should be in a range of 0.9 to 1.2 times the nominal thickness of the part. Designing part with rounded corners help proper filling of the part during the molding process. It also helps to eliminate the areas of high stress and possible breakage of the part. Let's see an example. So here you can see the correct and incorrect way of designing the part. The first one, which has the corner we have given a fillet, and the right side we have the sharp corners. So when we have the fillet, the mold will flow smoothly during the molding process, and it reaches all the regions faster than the other component. So here, to ensure the dimensional stability, a minimum radius of 0.25 mm is recommended on the plastic component. Next is the draft perpendicular to the parting line or draft angle. Draft is the amount of taper on the vertical walls of the plastic part. When you design, you must keep a draft angle perpendicular to the parting line so that the part will be easily ejected out of the mold. Without draft, the part may not eject out of the mold, and also it can undergo damage to the side walls of the part. Typically, draft angle varies between 0.5 degree to 2 degree based on the size of the component. It can vary based on the part restrictions and specifications. Here is an example of the draft angle. So you can see this component, the parting line is in the middle, and this is the core and cavity is mating in the parting line, and the draft angle provided in the both the surface will help to check the part once the molding process is done. Next, inclusion of ribs. Inclusion of ribs needed to help reinforce the plastic strength. When you provide more ribs, eventually the plastic will have more load carrying capacity. Depending upon the material used, rib thickness should be between 50% to 70% of the part thickness. This is required to avoid seam marks and other plastic defects. Here is an example. You can see the ribs are maintained inside the plastic component to have better strength, and also this helps to reduce the thickness of the overall part and enhance the mold flow, because if you make the part to increase the strength, you don't have to increase the thickness of the part. Instead, you will be adding more thinner ribs across the part. Next is mold shrinkage. The shrinkage that occurs during the plastic part molding process can be as much as 20% of the volume. So when you design the mold, you have to consider the shrinkage allowance as well. Crystalline and semi-crystalline materials are most prone to thermal shrinkage, and amorphous materials are known to shrink less. So you can reduce the shrinkage by adjusting the resin formulation or adjust the mold design to get the dimension you want based on the expected shrinkage calculation, and also optimize the processing parameters such as molding temperature and pressure, injection speed and time to get more accurate results. You can see in this image the defects caused by shrinkage. It could be the voids formed inside the plastic component or the seam marks or warpage. Next is hole design. The location of the hole on an injection molded part can have a significant effect on the cost and quality of the component. Hole consideration is dictated by the functional requirements of the part and its end-use environment. Every effort must be made to locate the holes in the right direction. You can see the left side image, the number of holes A, B and C. When you consider the manufacturing of the part, it has to be the hole A should work because it may be a extra feature in the mold cavity, whereas hole C require a side action to withdraw the core pin from the hole and allow the part to be ejected. So there is an alternative way. Instead of making the hole C, you can still make the hole B with an extra material removed from the top of the surface. Also, the hole to hole thickness to be 2 times the thickness of the part. Also, the hole location or a hole spacing is also important. The hole spacing, the recommended hole spacing is 2 times the thickness, and the distance of hole edge from the outer edge should be 2 times the thickness or the diameter of the hole. Here is an example of correct and incorrect way of making a hole, specifically for the inserts maybe. you don't want to core too long. Instead of that, you have to have the material in order to maintain the strength and rigidity of the component. Next is niche lines or weld lines. Weld lines are the weak points where the material flows together when a core pin blocks the normal path of the molded material as it enters the mold. The weak point occurs on the back side of the pin where the material flows together. It can be eliminated by proper placement of the gate or material entry point. Design part carefully to avoid unnecessary coring. With coring, it is very important to specify the location of the part where the niche marks cannot be tolerated. This will eliminate potential problems in the mold design stage. So you can see the pins actually causing the formation of weld lines. Next, special features. The plastic part should be designed so that the mold tool open and eject the parts easily. When special features like holes, undercuts or shoulders prevent the release of the part from mold, it may be required that the side actions to be incorporated into the design. The side actions pull coring in the direction other than the direction of the mold separation. So these extra features and side cores and things will help to create the cores and holes and other features, but eventually it increase the cost of the product because tool cost is going to be much higher. As a thumb rule, parts with external features need to be designed so that the part can span across the parting line. If the part cannot span across the parting line, slides are needed to generate the feature. Also, the direction of pull must be considered in the plane that will be pulled within the sliding steel. And next is inserts. The inserts made of steel, brass and aluminum components are commonly inserted into the plastic parts during or after the molding process. There are a lot of standard inserts can be purchased from the market and incorporated into the mold. You can see this image. The inserts are already assembled into the part, and you'll be able to see the type of inserts in the right side image as well. That's all the major guidelines for the plastic component design. I'll be uploading a couple of other videos as well. Please share your comments and suggestions. Thank you.